Good morning. My name is Farhan Hatem, registration number 20BME0246, and today I will be giving a brief about the research topic that I had chosen, which is the analysis of composite materials in rocket converging diverging nozzles. So first of all, we have to understand what a nozzle is. So it is so sort of like a nozzle is often best described as a sort of pipe or a tube which has different cross-sectional areas, and its main purpose is to modify the flow of a fluid. It can be liquid, it can be gas, and these nozzles can be used to control the flow rates, the speed, the direction, and even the pressure of the fluid stream that comes out of the nozzle. Um, so in the case of rocket engines use nozzles to accelerate the hot exhaust gases that are formed because of combustion, and use this to produce thrust. Rocket engines have a fixed geometry CD nozzle or a converging diverging nozzle, and in rocket engines the diverging section is much bigger than the converging section. Now, because the nozzle conducts hot gaseous exhausts, right, there can be interactions between this hot exhausted gases, and because of temperatures, it can react with the materials inside the nozzle. It can react with the nozzle materials or inner coating, and this can cause chemical interactions which could possibly damage the material. So it is important when designing these nozzles to choose a proper material, and research has often been conducted in using composites to design the interiors of nozzles, because one, they are lightweight, and two, they're also very economical, and three, they also have shown good mechanical properties. But we'll be discussing and seeing what sort of composites were used, and especially what different materials were considered before moving on to these composites. So first of all, we have to understand why there should be a need for such these materials. We need so the nozzles need to have a good interior material just to prevent what we can say as is nozzle erosion. So erosion mechanisms, technically we can classify them under three. So that is the melting. Melting can happen because of hot exhausted temperatures. Then oxidation can happen, and also mechanical abrasion. So in general, the erosion characteristics of materials when they are exposed to hot gases of rocket fuel, right, can be related to material properties in thermal and chemical environments. These relations are described for certain materials which are chosen for studies. So the first type is refractory metals. So in certain studies, dense refractory metals were found to be the most erosion resistant materials. One of them was molybdenum, and molybdenum did not erode when in the case of two propellants which were considered to be as low temperature environments, but it was seen to erode extremely in the case of very high temperature propellants. And in general, high density tungsten nozzles, which is also type refractory, perform was also experienced certain amount of erosion even in case of a low temperature or a medium temperature propellant. Now, to understand why these metals often showed failure, it was often described the phenomenon because the molybdenum did not erode with the most oxidizing fuel or with a relatively abrasive intermediate propellant. So this says that molybdenum is not particularly susceptible to oxidation except at extremely very high temperatures. Uh, Coming back to the tungsten nozzles, erosion was seen to take place in like a different medium temperature propellant, and this propellant or fuel was again like a low to medium temperature based propellant. It was also the most oxidizing and also the least abrasive in environment, and can be noted that the tungsten did end up failing mainly because of the mainly because of the oxidation that occurs. Low density tungsten nozzles did fail catastrophically when it came to high temperature nozzles. Again, the main reason was seen to be oxidation, but certain factors like mechanical abrasion also contributed to it. Then moving on to another type, that is refractory compounds. So those are refractory compounds chosen for this. So they were refractory metal carbide, some certain graphite combinations. Then another type called refractory metal carbide materials. Then metal impregnated refractory compounds, which included cermets, and a silicon nitride, which is a type of ceramic. Now, the refractory metal carbide, graphite, did not show any sort of erosion with the medium temperature based propellant, but it did show catastrophic erosion when it came into contact with high temperature propellants. But there was one material which is called tantalum carbide, which comes under this metal carbide family. This tantalum carbide only showed very slight erosion despite it being a medium based, despite it being high to medium to high temperature based propellant. And going through the results of this shows that erosion came primarily from the oxidation, and it increased with the increased severity of this oxidizing environment. Then the refractory metal carbide tungsten nozzles actually displayed very good performance against erosion and was able to survive uh, in like high temperatures when compared to that of other refractory metal nozzles. However, it was seen that there were some certain instances of thermal stress cracking. Then another carbide, which is silver infiltrated columbium carbide tungsten material, only eroded slightly with medium base temperatures, but it eroded catastrophically with a more oxidizing propellant. Um, then moving on to the other type of materials, that is the cermets and silicon nitride, which is the ceramic. So then these nozzles eroded only slightly, again with an oxidizing propellant, but it also experienced catastrophic erosion with very least oxidizing propellants. Then moving on to graphites, pure graphites. Graphites in general showed very poor erosion resistance, and that is they degrade very easily when comparing to the refractory metals. Thus, it is also shown that oxidation was the major mechanism of failure in the case of graphites. And along with oxidation, we could also see mechanical abrasion was a contributing failure mechanism. If mechanical abrasion contributes to failure, then the erosion will be expected to diminish with reduced chamber pressure, and the erosion rate was diminished for two of the graphite materials is evident from pressure traces in which the pressure regression is relatively flat in the lower pressure region as compared to high pressure operations. Then coming to fiber reinforced plastics, uh, a very heavy erosion occurred by ablation in the case of fiber reinforced plastics, and this erosion severity increased linearly with as the temperature of the gases and flames increased. Again, coming to graphites, this fiber reinforced plastic will showed a low erosion rate with low pressures in the nozzles. Then, under thermal stress cracking, uh, amongst all these materials that were studied and investigated, the refractory compounds and the low density tungsten materials, which were used in nozzles, developed thermal stress cracks. Some of these nozzles cracked both radially and circumferentially, and so it was seen that certain chunks of the nozzles came off and it's separated. Silicon nitride and refractory metal carbide graphite cracked extensively. The refractory metal carbide tungsten nozzles cracked less than that of the previous one. Um, then, although the high density, so it was previously noted that the tungsten was in some way a bit superior, or can be said to be superior, but it definitely showed erosion resistance and also resistant to thermal cracking. What could be expected that is as we use propellants with very high temperatures, then it would also be seen that tungsten could also experience that the chances of these tungsten nozzles failing would also be a bit higher, especially if these temperatures were above 7,000 degree Fahrenheit, above 7,000 Fahrenheit. So could also be seen that in these cases the potential, so rather than this is that materials such as refractory metal carbides could be used, then in these cases they can be seen to perform well under in high temperature like 7,000 Fahrenheit, and these are developed and they can also be improved as well. And just as the high temperature would also affect the materials of the nozzle materials, the pressure developed in the chambers also play an extent. These pressures are developed because one due to the constricting areas as well and due to the very fast flowing gases. Certain investigations show that graphite and fiber reinforced materials had good erosion resistance at very low pressures, and hence when designing nozzles with low pressure, which are designed to operate at low pressures, then these materials could then be preferred. Then it can also be said that especially in nozzles such as the entrance to the nozzle, the throat, and even the exit places, the material losses can be better tolerated, and these two materials, fiber plastics and graphite, can be used extensively. So coming, so then in the case of the, so when designing a composite D-Laval nozzle, it was also seen that silica reinforced plastic were also being considered, especially for the ablative cooling in liquid and solid engine chambers. But the main issue with this is that the excessive erosion, especially happening in the throat, which is an important area of the nozzle, actually contributed to engine performance losses, since the throat is the area where the flow goes from a much more sonic velocity to a supersonic velocity, and hence if material erosion happens, the, the surface of the throat gets affected and hence flow can be disturbed. Um, so as engine sizes increases, the structural requirements also increases. Thus, in addition for an engine to be high erosion resistance, engines should also have the ability to, it's said that the engine should have a high char strength at low char rates to minimize certain weights. Then coming to certain results and discussions mentioned here. So if you were to maybe conclude, and then of course there were like certain studies conducted on these metals, and some of them were able to perform in low temperature propellants and high temperature propellants. Some of them did show high erosion resistance, and some of and and for some of them that did show erosion resistance, they also then some of them also showed cases where they succumb to thermal stresses. So if we were to conclude, so an investigation in so the paper which is referred to, so looking at the investigations, it evaluated certain samples of ablative materials to be used as on the interior of nozzle section with a particular type of fuel that was used throughout the investigation. It was seen that the lightweight silica material had higher erosion resistance than metals and non-metals, um, and the most erosion resistant materials was a lightweight high purity silica, and the least erosion resistant material was a heavyweight high purity silica. And then finally it was then concluded that the use of ablative composite materials are appropriate for the D-Laval rocket nozzles. Thank you.